Now, it turns out that there's this old paper from the 1930s by A.W. Conway, which shows that you can describe Dirac spinors, four vectors, and the field string tensor using nothing more than the complex quaternions. As you may recognize, this is already most of the Lorentz representations that we use today in the standard model. Okay, well, that's hopeful. But what I want to show you now is that there's in fact a bigger picture behind Conway's findings that is having to do with discrete symmetries. Now, this bigger picture will allow us to get a complete set of the standard model's Lorentz representations. This involves the inclusion of scalars and the selection of Majorana spinor representations over Dirac. And finally, this bigger picture will lead to an idea that might help us address the following question. That is, if all we have is an algebra, then how are things like the field string tensor and spinors supposed to pop out or emerge? So let's talk about that last point first. If all we have is an algebra, then how are things like the field string tensor or spinors supposed to pop out? Well, the bigger picture behind Conway's findings that I was referring to relates to the idea of an ideal. So let's say we were to have an algebra, and in this case, our algebra is going to be the complex quaternions. Then a left ideal is a special subalgebra whereby if you were to left multiply any element A of the algebra onto an element V inside the ideal, then their product, V prime, will always get pulled back inside the ideal. So loosely speaking, you can think of ideals as an algebra's version of a black hole, in that it's going to pull any element into itself via multiplication. So ideals are these stable subspaces of an algebra. Now, what we're going to find shortly is that each of the Lorentz representations of the standard model can be identified as objects that generalize the notion of an ideal. So in this sense, the scalars, spinors, four vectors, and field string tensor can each be seen to be stable subspaces of this algebra. For mathematicians, these are known as invariant subspaces under some action of the algebra on itself. Now, the idea that I proposed in my thesis is very much in the flavor of Darwin's mechanism for survival of the fittest. The fact that these ideas are stable under multiplication could be viewed as them surviving over time. Now, you'll notice that in this example, we assumed that multiplication was given by left multiplication, but we could just as easily have used right multiplication, or perhaps something slightly more elaborate like an adjoint action. So what I'm about to show you is that scalars, spinors, four vectors, and the field string tensor, that is the various Lorentz representations of the standard model, can each be thought of as generalizations of ideals under different multiplication rules. A more precise way to say this is that each of the Lorentz representations of the standard model can be shown to be invariant subspaces of the complex quaternions under some action of the algebra on itself. So this next part is going to be important because we're going to reuse these same generalizations of ideals later on in the talk.